Let's walk through some calculations of osmolarity. In a recent blog and video, we explained the concept of osmolarity, including how to calculate in 4 easy steps. Now we'll put it into practice. Let's calculate the osmolarity of 1 liter of normal saline, which is a 0.9% solution of sodium chloride. Sodium chloride is an ionic solute. Ionic solutes will dissolve to form ions. These ions maintain some degree of attraction to each other, which is represented by the osmotic coefficient. For sodium chloride, that is 0.93. Calculating the osmolarity of an ionic solution begins with calculation of equivalent weight, which is the weight of 1 mole of an ionic solute. It is calculated by dividing the molecular weight by valence. If you need help with calculating equivalent weight and determining valence, head over to pharmacology.com and search for milliequivalent for a full unit dedicated to this topic. You need to first know how to calculate equivalent weight before you can calculate osmolarity of ionic solution. In this example, the molecular weight of sodium chloride is 58.5 grams and the valence is 1. Once we know our equivalent weight, we can calculate the number of moles by dividing our given weight by the equivalent weight. 1 liter of sodium chloride is 0.9 grams per 100 ml of solution, or 9 grams per liter. Our given weight is 9 grams divided by our equivalent weight of 58.5 grams gives us 0.154 moles of sodium chloride. The next step is to convert the number of moles to osmoles. Remember that ionic solutes maintain some degree of attraction to each other in solution, and that the osmotic coefficient represents the degree of interaction between them, 1 being the ideal of no interaction. Anything less than 1 indicates the influence of factors like concentration and ionic strength. In an ideal solution, each mole of sodium chloride will dissociate completely in solution and exist as 2 individual ions of sodium and chloride, but their opposing charges maintain some attraction between them. To calculate the number of osmoles, we multiply the number of moles by the ideal dissociation into ions and the osmotic coefficient. So in our calculation, we assume complete dissociation of sodium chloride into 2 separate ions. Then we account for the interaction between these 2 ions by multiplying by the osmotic coefficient of 0.93, and that gives us the osmotic pressure for each mole of sodium chloride. We already know that we have 0.154 moles in 1 liter, so the osmotic pressure in 1 liter is 0.286 osmoles. The final step is to express osmolarity in milliosmoles per liter versus osmoles per liter, which simply requires multiplying by 1,000 for a final osmolarity of 286 milliosmoles per liter. For a step-by-step guide to calculating osmolarity, head over to pharmacology.com.